We have seen a glimpse of several algorithms in TCP. There are more. Some even are being developed, so there probably will be new ones in the coming years. But with the rake philosophy, the idea is to give you a hint, a fairly detailed explanation of some of them. Now we'll come back to more fundamental things. Why does TCP do things the way it is? We have seen that with TCP, we correct packet losses end-to-end. It is the source that detects whether a packet is lost and retransmitted. But we have seen other mechanisms in the MAC layer where things are a bit different. When we talked about Wi-Fi, in Wi-Fi we've seen that if one of the links on my path is Wi-Fi, if a packet is lost between the two ends of a Wi-Fi link, there is an ACK in Wi-Fi and we will retransmit it. So in some cases we do a retransmission locally, we call it hop by hop. In other cases we do it end-to-end. So why is it like this? What should be the optimal? Is TCP vastly suboptimal? Should we expect it to be changed when things become closer to optimal or not? That's the question we will address now. So this is what I've discussed. With TCP, we repair the packets end-to-end, but we could imagine, and we have seen that in the case of Wi-Fi, this is done hop by hop. So we could imagine a system where routers detect losses and repair them. After all, that would be better for customers. In fact, the very first computer networks, which were the IBM networks, they did that. I worked at IBM at that time, and one of the things our management said that with IBM networks, we never lose packets. So it's much better than the internet because the internet loses packets. So we never lose packets because every intermediate system puts sequence number when it talks to a neighbor, and every packet is followed and ACKed, and if one thing is missing, it's retransmitted. So in fact, truly, the IBM networks of the 80s never lost packets. But that was not in the history of evolution. They were not the winners. So they are the diplodocus of computer networks. So let's examine the arguments, whether one should do one or the other. In the internet, there is something called the end-to-end philosophy. That is a thing we've seen already when we discussed packet switching. We'll come back to it when we discuss the application layer. That's one of the driving architectural principles of the internet, which says that anything that can be done end-to-end should be done end-to-end. The intermediate systems should be as simple as possible. In particular, routers should just very quickly send packets wherever they have to send them, but not do anything intelligent about the packet. That's the principle. The practice, I will say, is a bit different, but that's called the internet principle. Now, if we follow this principle, we should do packet recovery end-to-end, like we do in TCP, and that was, I think, the reason why they did it in this way at the beginning, because as we've seen, TCP is fairly complex, so repairing packets with all the sequence number, fast retransmit, all that stuff is better done in hosts than in routers. There is also originally another argument, which is visible on this animation. What is this showing? Well, it's showing that the packets are not following all the same path. So if you ask router R3 to know whether a packet is lost, then it will not know whether a packet is missing because it's following another path or because it is truly lost in between. So it might be practically very difficult. In practice today, it's very rare that packets of the same TCP connections follow different paths, truly between routers. Routers will try to avoid this in order to make the reordering as small as possible so that the TCP reordering heuristics work well. So this is what designers of routers today will try to do. At the beginning, it was possible. The internet was truly a datagram system. It could work any case. So we have here good reasons to do error recovery and in the end systems only. Now let's understand other arguments. Now, this argument has to do with what is called capacity. A channel is something where you put packets on one side and you receive at the other end, or more generally, information. Some of you may take the information theory course or had some hints of information theory course. Every channel, when you're able to model it as a stochastic system, has what is called a capacity. What is the capacity of a channel? It is in the ideal case, how many bits per second you can transmit in the channel. And more accurately, you cannot reach that many megabits per second, but you can come as close to it as you want. So it's the least upper bound on the capacity of the bit rate of the channel. So when we say we have a channel, the capacity of a wireless channel, for example, is 200 megabits per second, then that means if you engineer a good transmission system, you should be able to get close to that capacity. And one of the beauties of information theory is that we're able to compute the capacity of a channel without knowing exactly how to build a coding system that will achieve that capacity. So we know, for example, on wireless channels of a given bandwidth, we know what is the maximum bit rate we will ever achieve. If you want to get more, you need to increase the bandwidth. There's no point in trying to find more intelligent ways of transmitting information. Here in our case, we have a very, very simple information theory result that has to do with what is called an erasure channel. An erasure channel is a channel that has a given nominal capacity, R packets per second. Assume, to simplify here, all packets are the same size. And assume this channel loses packet with a probability P. And assume that with a probability P. Then, with some statistical assumptions, for example, if the losses are independent means whenever a packet is sent on this channel, you flip a coin and you decide whether it's lost or not. If losses are not independent, that could be, for example, you flip a coin and you decide to kill 10 packets in a sequence. That would create losses that are not independent. But to simplify things, assume losses are independent. If that is the case, then information theory tells us that the capacity of such a channel is simply the nominal capacity discounted by the loss. So if I have a channel at 10 megabit per second and a packet loss probability of 10%, the capacity is 9 megabit per second in the sense of Shannon and information theory. In this particular case, it is a very simple result. Information theory is about more complicated cases. In this simple case, it means if you have a smart coding system, you should be able, on a system that loses 10%, to achieve a lossless channel of 9 megabit per second. And in fact, the solution in this case is to have TCP with an infinite window. So if you retransmit simply packets that are lost with a smart, theoretically smart loss detection scheme, you will achieve that capacity. In reality, with TCP, you'll have a finite window. Your error detection is also not perfect. Sometimes you will retransmit where it was not necessary. So in practice, you will get a bit less. But in theory, that's what you could obtain. So that is for the concept of capacity. So now, let's examine what is the capacity of an end-to-end path if we use end-to-end recovery versus hop-by-hop recovery. So here's a very simple toy example. I assume I have a path with a number of hops, and each hop has the same transmission rate and the same loss probability. And there are k links in total. This is very simple. In the internet, of course, you don't have a fixed capacity just for you. The capacity you have depends on how the bit rate is shared between different flows, and how this is done we will discuss in the congestion control part, but assume this here. And the question is, what is the capacity with both systems we have seen? If I repair losses end-to-end, or if I repair them hop-by-hop. So let's start with hop-by-hop. Hop-by-hop means we send A sends a packet to R1. R1 checks if the packet is received. If it's not received, it will do a retransmission and whatever is needed to make sure that the packet is correctly, the loss is correctly obtained here. While we do that, if, for example, R is 10 megabit per second, the capacity of this single leg here is 9 megabit per second. Right? The capacity between A and R1. And the same between R1 and R2, etc. Now assume there are potential losses everywhere, and we do hop by hop. That means all of the systems do this repairing of losses. They implement something like TCP to number the packets and repair it. If we do that, and we'll ask now the question, I look at all the thing as one big channel, what is its capacity? How many packets per second can be sent in the best case from A to B? And the majority says A, but this is wrong. The correct answer is B. Let's see why. We do error recovery at every hop. That means the line between A and R1 has a capacity of R1 minus P, 9 megabit per second. Between R1 and R2, we also have 9 megabit per second. Between R2 and R3, we also have 1 megabit per second. It's easy, or at least intuitively clear, that if you daisy chain, if you pipeline a number of systems that are at 9 megabit per second each, then you have a 9 megabit per second avenue at the end. So the capacity is in fact the minimum of the capacity of all the links if each of the links is lossless. So we make it lossless by doing error recovery. We reduce the capacity, that's the price to make it lossless. And then the capacity is the mean. The mean of R1 minus P is exactly that. Most of you gave this answer. Well, this answer is in fact the capacity of the path when we do end-to-end recovery. When we do end-to-end, that means we have one big channel over which we repair the losses. And what is the loss probability over this big channel? The raw nominal rate is capital R, is the same. What is the loss probability? Then the loss probability is 1 minus the non-loss probability to the power k, if we assume the losses on all the different legs of this figure are independent. The probability that a packet is not lost is a probability it's not lost anywhere in the k hop, so 1 minus p to the power k. So that gives us a capacity R1 minus p to the power k. So this thing is the formula if we do end-to-end recovery. Which one is the larger? Well, here we have 1 minus k to the power k. This is smaller than 1, so this will be smaller than this number. For example, if k is equal to 10 and the loss probability is 5%, the end-to-end capacity is 60%. Because there is 40% probability that the packet is lost at least somewhere. Whereas if we repair hop by hop, then the capacity is 95% here. If the packet loss rate is minuscule, here 10 to the minus 4, we see that doesn't make a lot of a difference. The capacity is quasi the same. So take-home message, well, if the packet loss rate is high, it's not a good idea to do end-to-end loss recovery. If the packet loss rate is very small, it doesn't matter. So since end-to-end is smaller, it's better to do, simpler, it's better to do it. How can we reconcile the things in the internet? What would you conclude from this? Well, if you have a link somewhere that for some reason might have a larger error rate, you will do local error recovery. So that's why Wi-Fi does it. This is why if you have a satellite link, you will do some mechanism to repair packet losses on the satellite link, because we know there are bursts of time, periods of time during which the loss rate can be high. If you're on cabled systems where the loss probabilities are very small, you don't do it. And this is how the internet is organized. The internet does typically error recovery end-to-end, does it always, and wherever else it's deemed necessary because we think the error rate is large. This is why it is done in this way. Voila, that's all we will see, at least for today, with TCP. We'll talk about it again tomorrow morning. And Lab 3 will give you an opportunity to exercise TCP and UDP. And in Lab 3, you will be able to see more convenient things that So in the lab 3, we will do low-level programming. So we will ask you to program using UDP sockets and TCP sockets. This is what you do when you develop systems. If you do web applications, typically you don't do that, and you use higher-level primitives. Higher-level primitives are application layer frameworks that hide the ugliness of TCP. And TCP is nicer than UDP because it does not ask you to retransmit packets. But as we have discussed, it has ugliness due to the head of the line blocking, due to the fact that it's a streaming thing. You don't know when you receive something whether you have received all the bytes, all that stuff. So there are higher-level framework. One of them is QUIC that we'll discuss a bit later. And another one that is much simpler than QUIC is called WebSockets, which is simply putting higher-layer Python primitives to avoid seeing a lot of the complexity of TCP. Voila. Any questions on TCP? Then we move on to the next topic, which is a simpler and shorter topic called multicast. Multicast is simpler, not so much because it is simpler per se, but because it is deployed only in very specific environments. So the evolution of software engineers has not bombarded it with lots of complexifications. Here I'm illustrating typical uses of multicast. Multicast was designed in the internet at the origin to be a replacement for TV and radio distribution over the air. The thinking was the radio channels radio frequencies are shared resource. It's very expensive. It's stupid to use it for broadcasting radio and TV. You better broadcast that by cables using the internet. So that's the system. And how now radio now is most of the time not broadcast using multicast, but using servers, where you connect to a server, but when you, for example, if this radio program here uses that kind of, or that one uses that kind of servers, sometimes when you connect to it, you see, oh, I cannot connect because there's not enough resources on the server. Because we know that if you do packet switching, it's much more efficient in terms of resources. If you do application layer forwarding of data, it's much more complicated. If 1 million people are listening to France Inter, then the server needs to handle 1 million sessions. So you need a server that's very scalable, and radios public, like France Inter that live on public money, they don't have the money to pay those million servers, so sometimes they hang. Multicast was made as a way to avoid that problem. Multicast is today mostly used in local area networks, like we have seen lots of appearance of multicast when we've discussed ARP and solicited node multicast address with IPv6, for example. But it's also used in industrial environments, typically process control. If you have a sensor that is sending information, typically you send it to a server that controls the process, but you may also have a SCADA or a monitoring system that is also watching everything that's happening. So you typically have in industrial environments the need for multiple systems to watch the data, to receive the data. One way is to have all the sensors send the data to different systems, or to create an intermediate server that receives everything and dispatches it to other systems. But there is a simpler way, which is to use multicast. When the sensors send data, they send it to a multicast address. And then who gets it depends on, does not depend on the sensor, but on the servers themselves. So IP multicast is associated with IP multicast addresses. So there is a fraction of the space of IPv4 and IPv6. With IPv4, it is these blocks of address. With IPv6, it is anything that starts with FF00. Those addresses have nothing to do with the other IP addresses. They are multicast addresses. They have nothing to do because they are logical. They are not associated to an interface like with IP. Normally with IP, an address has a topological meaning. It is located in a subnetwork, inside a larger network, etc. Multicast addresses don't have that meaning at all. They are purely logical. They are like radio channels. You tune to a given radio channel. It's the same thing here. You tune to a multicast address. There are two types of uses for multicast. The standard way is any source multicast, and the most convenient way is source-specific multicast. Any source multicast means the group multicast address, the multicast address identifies the group. And it's an open group concept where any source IP address can send to this group. Source-specific multicast means the group is identified by the combination of a multicast address and a given source. So what is implicit here is we expect only this source to send to this multicast address. Or more specifically, more exactly, in order to obtain the data that are sent to a multicast address, it is the destinations, the receivers that need to do something. Remember, the mental model is that of TV or radio distribution. If you're a radio sender, you send a signal in the air, and that's all. If you want to receive, you need to tune to a given frequency. It's the same with multicast. If you send with IP multicast, you send the data to the multicast address. If you receive, you need to instruct your router, as we will see in a minute. You need to instruct the internet that you want to receive. If it is source-specific multicast, you say, I want to receive the data that comes from this source to this multicast address. If it's any source multicast, you just specify the multicast address. Here is an example that illustrates practically everything in one slide. I'm showing here one source that is sending to a number of receivers. So the source simply sends IP packets by sending them to the multicast address. In the lab, you will see that in order to specify a destination address at multicast, you still need to instruct your, you may need to do some special things. But essentially, there is nothing else to do other than give a destination address, like in any IP packet, where the destination is a multicast address. If nobody is listening, this packet will simply die at the next router. Because for multicast to work, for multicast to work, we need that the destinations do something explicit. With IPv4, it's called IGMP, Internet Group Multicast Protocol, or something like this. Internet Group Management Protocol, sorry. And it means that whenever A wants to receive the data sent to this group, so this is showing source-specific multicast, SM, it sends an IGMP join message. IGMP is a protocol like ICMP, except it's for groups. In IPv4, it's a separate protocol. We're used to that. In IPv6, it is a different one. It's called MLD, Multicast Listener Discovery. And the goal of this is for a host to signal, in principle, to your default router. You say to your router, I would like to receive the data of this multicast group. Now, for the thing to work, you need that the routers in your domain implement multicast routing. They must propagate this information towards the source here. So the router keeps state information. It says, oh, there is someone on this interface that would like to receive that stuff. And now it will propagate this information towards the source. So R1 will talk to R2 and will say essentially the same thing, except now it's the multicast routing protocol that does it. A routing protocol is something between routers. So it will say there is somebody in R1 that needs to have this information. Therefore, R2 will find a path towards the source. It will speak to R5. Now, R5, R2, and R1 know that they should deliver this data, and they know on which interface they have to deliver it. So now, when S sends the next packet, it will be delivered along the multicast tree, and it will be delivered to A. Now that's all. This multicast group has only one receiver. That's not very exciting. You expect a multicast group to have millions of receivers, not one. Assume at some point in time later, B also wants to listen. So B will do the same thing. R4 will join R2, will add some state information, and will inform R2 that there is someone else who needs to receive the information on another interface. So those red blocks are simply state information. So the routers now need to keep state information. And the thing here will stop here because R2 knows that it is already receiving this information. So R2 will not speak to R5. R2 only knows that. And it has two blocks of information because it has two interfaces on which it has to distribute the data. And the next packet sent by S now will go from R5 to R2. And we see that it is R2 that will now has the job to duplicate the data. That's the trick of multicast. It is the intermediate systems that duplicate. It's a good trick from one viewpoint. What's the benefit of doing that? Scalability, exactly. If you have a source that has 1 million receivers, right? And if you have a number of routers that do it, if along the path there are 10 routers that each duplicates the packet, at the end you have 2 to the power 10, which is 1,000 packets. Right? So if you have 20 hops, you have 1 million receivers by simply having every router copy one packet, make 2 packets out of 1. So the job of every router is small. It has a small duplication to do. But if you do it along a tree, at the end you have a huge multiplication by the virtue of exponential growth. That's the idea. That's the benefit. That's the intention of multicast. By having the multiplication done along the path, nobody does a great job of packet multiplication. And in particular, the source. The source sends only one packet and reaches 1 million destinations. So the source has only one socket. It's sending, typically with UDP. TCP does not work with multicast. And so it has a simple socket. It sends. So the job of the source is very easy. So if we use that, we will not have servers that are exhausted because their job is so ridiculously simple that there's no reason for them to be exhausted. Now, of course, there's a price to pay. That routers, multicast routers, have to keep state information. Now, this is in contradiction to the end-to-end principle and the design of the internet. In the internet, we want routers to be as stateless as possible because they are the bottlenecks of the internet. So, what does a router need to do? Well, a router needs to remember for every multicast group, whether it's source-specific or any source multicast, what are the what are the outgoing interfaces? That's the main thing it needs to do. Typically, you do also packet filtering. For security, you check that the packets are coming where you expect them to come. So that will at least give a small mitigation under a number of attacks. And you also need to run a routing protocol. So a routing protocol typically requires other information. Worse, because multicast addresses are purely logical, there is no way to aggregate them. This is illustrated in this figure here. In this figure, we have Lisa and Bart that are listening only to M2, and Homer is watching both M1 and M2. He's probably not watching both at the same time, but he has the 2 windows open on his screen, and we know we all do that. Then we see here the multicast routing information that's present in router R1. Then it has one entry from M1 and M2 with the list of outgoing interfaces, and a similar thing here. So we see that we were able to aggregate, for example, here all of the B network as one single entry for unicast forwarding. But for multicast, we're not able to do that. So we need state information. And this is why multicast does not scale to the global internet. This is why it's not deployed. You cannot use multicast over the global internet, at least today. One of the reasons is this one. There is a fundamental scalability problem. It is deployed, for example, in TV distribution networks. Swisscom uses multicast to do the distribution of the live TV channels. So if Swisscom sends 250 TV channels, it has only 250 sockets in one server to send them. Of course, this is a very small economy because in reality, you want to be able to access your TV or your radio program on demand, so you don't want to listen now to what is sent now. So you still need servers, and this is why multicast for TV distribution is not very popular. But as I mentioned, in industrial networks like smart grids, this is very frequently used. We have seen multicast at the IP layer. Now, of course, the IP systems will be interconnected by things like Ethernet or Wi-Fi, so there is a need for address resolution. How do we go from the IP addresses to the MAC addresses? Is there something like ARP? Well, the answer is no. For good reasons. You cannot send a query, a request, and who has this MAC address corresponding to this group, because the group might be anywhere. So instead, there is what is called an algorithmical mapping. That means that there's a deterministic rule that says if the destination IP address is a MAC address, is a multicast address, here is automatically how you can deduce what is the MAC address that corresponds. For IP address, IPv4 addresses and IPv6 is done differently for some reasons that to be honest, I don't know. For IPv4 and IPv3, we use different reserved prefixes in the space of MAC addresses. This is the reserved prefix for IPv4. This is the reserved prefix for IPv6. And the rules are, for example, I'm showing here for IPv4. If you have an IPv4 destination address, you translate it into hexadecimal because MAC addresses are written in hexadecimal. You take only the last 23 bits, which you retranslate into hexadecimal, and you populate the last 32 bits with that here. The last 24 bits with it, which gives this thing here. Why it's done this way, not very clear. In particular, there might be collisions. There might be multiple multicast addresses. IP multicast address may collide to the same MAC address. We've seen similar things when we've talked about the solicited node multicast addresses, which are specific cases of multicast address here. If that happens, then you might have the hardware, the Ethernet adapters or the Wi-Fi adapter, might receive packets for a group on which nobody is subscribing. Right? But the hope is that this happens rarely. Last, at the MAC layer, multicast is either ignored, handled as broadcast, or if it's truly handled, it's treated as any source multicast, because the MAC layer doesn't want to bother knowing what is the source IP address. Those mappings here ignore what is the source IP address here. The result is that if on the same TV distribution, for example, you use different sources and different groups, if different groups of different sources have the same multicast address, there will also be a collision here. I said that in the best case, multicast is treated at the MAC layer the way by making distribution trees. In reality, so indeed, if you have what is called a non-smart multicast switch, it will simply treat things as broadcast. So this is shown here. If this non-smart switch, so this would be the small switch for 50 francs that you buy at Migros, if it sees a MAC destination address that is of the multicast type, because those types are predefined, there is one bit, well, the IPv4, IPv6 are, the addresses used for IPv4, IPv6 are predefined, but in general there is one bit. The 8th bit of a multicast address must always be 1. So the switch knows it's multicast. If it knows, I know it's multicast, and I know I am not smart, it will simply broadcast it. So the printer will receive your video packets, for example, if you have such a switch at home. But the printer will discard them. It will see there is no process on my machine that is receiving it. It will discard. If you have a smart switch, it will try to build a distribution tree and send them only to the systems that have done a join here. How can it do it? Well, in principle, there is no layer 2 mechanism for doing that, in principle. A smart switch is something that violates the layers. So a smart switch will look at what is required from this system here, for example, by sniffing all the IGMP packets. If it sees that this guy is sending an IGMP request for this group, it will say, oh, I need to transfer the data here. So it will do layer 3 job, and we still call it a layer 2 switch, but in reality it is learning from layer 3. That's one of the things that a smart switch can do. If that's the case, your printer will not receive your video. But those are typically higher-end switches, the Cisco switches that cost a few thousand francs. We'll do that kinds of things. Last, how is the magic happening in the network? How is multicast routing working? So multicast routing is one of the places where multicast is not very simple. There are many, many multicast routing protocols, but the evolution has sorted things out, and only one of them, PIM-SM, has survived. So PIM stands for Protocol Independent Multicast. The independence of protocol is with respect to the unicast routing protocol. Next week, we will start discussing of unicast routing, which is how the different routers in the internet in general, how they know where to send packets. The major job is for unicast routing. Some multicast routing protocol do their own thing. They say, and for multicast, we need another way of doing things. PIM is a very economical system that says, I assume that the routers already know how to route packets from A to B for unicast. And I will use this information to do my job. How does it do? By using what is called simply reverse path forwarding, where the idea is very simple. It's very simple to understand if we do source-specific multicast, which in my opinion is the only reasonable use of multicast, even though in the lab we will ask you to do some funny any source multicast. But for security reasons, if you deploy multicast in a system, you want to make sure that not everybody can send to the multicast group. Why would you like to enforce this? Well, assume you work for FSB or the organization of a country that is in charge of doing cyber attacks. Cyber attacks are much easier if some people are using multicast, and you can inject into multicast trees some packets, right? By sending one single packet, if your multicast group has 1 million receivers, like a Swisscom TV thing, with a single packet, you can hit 1 million Swisscom boxes. So it's bingo for the attacker. It's much easier. So multicast, of course, is very powerful. It's powerful for the sources, but also for the attackers. So what you would like is to control who the source is. It's very easy to control if you have source-specific multicast. All the packets all the routers on the path can always do one thing that is called reverse path checking. When you receive a packet, if you're a well-behaved router, the main job of a router is forwarding a packet according to the routing table. But if you buy a high-end Cisco router, it will do lots of security checks. One of the security checks is, this packet that is coming on this interface with this source address, does it make sense? Is it normal that I see in this direction? By, for example, asking if I would send things back, do they go also this direction? So you will do typically that kind of thing with source-specific multicast. So this is why source-specific multicast is preferred by operators the few operators who run it. The other benefit is that with source-specific multicast, PIM-SM is very simple. Remember R1, the job of R1 was to receive the IGMP join and start building a multicast distribution tree. Now, a very simple thing to do is to simply go back to the source, because you know I join S. So what R1 will do, it will send a PIM packet in the direction of the source. So it will send it not to S, but it will look at its IP routing table, its forwarding table. It's in order to reach S, in which direction should I send this packet? Here for R1, of course, there's not much choice. For R2, perhaps the question is more relevant. R2 needs to forward the PIM message. So R2 knows in order to go to S, I have to go to R5. It knows that from its routing table. So it will send the PIM message that has the job of creating the tree to the next hop given by the routing table. Of course, the PIM message not sent to S, but it sends towards S. So this is why it's called protocol independent. It's protocol independent because the only thing it needs is that the routers have a forwarding table. How the forwarding table is done, they don't care. We will see in contrast another protocol called OSPF next week that is able to build multicast trees natively inside the routing protocol. Here, this is not what is done here. So this very simple thing gives us the operation of the protocol. Of course, that doesn't kill the difficulty, which is that the routers need to keep state information. I mentioned the security aspects already. So imagine you are an attacker and lots of people use multicast, and it's wonderful for you. Your life will be much easier. And this is probably the reason why multicast is not deployed in public internets. It's deployed in things like Swisscom TV, but it's something that happens between the TV box and Swisscom. It's not a service that is available to you. Although if you hack a bit your TV box, you could have access to multicast. But if you write a multicast application, it will probably not work. It doesn't work on the EPFL Wi-Fi network. This is why when you will do the multicast lab session, you have to use our multicast, our Wi-Fi infrastructure in INF 019. It works on the EPFL wired network, I believe, at the last time we checked. Multicast is also not very secure because, like ARP, NDP, IGMP, MLD, they are not secured, right? So if you deploy this commercially and you're serious about it, you will need to do a lot of additional mechanisms, which are essentially intrusion detection mechanisms. You need to observe everything and look for anomalies. And when anomalies occur, you have to kill the traffic that you think is not regular traffic. So multicast-capable networks have a high cost in exhaustive filtering and monitoring tools, which in some sense may defeat the purpose of the simplicity of multicast here. But, as I said, it's done in private networks, TV distribution, smart grids, process control, factory plant automation, all systems where then the benefit is, if you deploy a sensor, the sensor, all it needs to know is what multicast address it has to send data to. Sensors are typically many and not very easy to manipulate, to log into and change things into them. If you add a new SCADA that is observing your data, you don't need to change all the sockets and all the sensors. You don't need to reprogram them to send to someone else. And you don't need an additional server to broadcast the data. That would be a single point of failure. I mentioned that multicast works only with UDP. Why is that? It would be very convenient to work with TCP. We send video distribution. If a packet is lost, we'll need to handle the loss. So, yes?
Otherwise, this will need to maintain a connection for each client, which defeats the whole purpose.
Exactly. TCP requires a connection, and TCP would require a connection with every client. So either we use TCP as it is, and then we have collisions. We break the semantic of TCP. What does an acknowledgement mean? Who sends an acknowledgement? Some receivers might have received something, some receivers not. So what happens if packet is received by A and not by B? How should the acknowledgement be sent? So TCP, as it stands, is not made for multicast and immediately breaks if you use multicast. So you could use one TCP connection per receiver, but as you mentioned, then you might as well use unicast if you do that. Plus the purpose of multicast is to send the same data to all. So even if we would find a way to make it scalable with 1 million connections, I need to repeat a packet, but only for some destination. Reliable multicast exists, and they use things that are called things like Reed-Solomon codes, where you send incremental parities that are able to repair losses, different losses for different customers. But that's another story, and I will not talk about it. That's all for today. See you tomorrow.